So today we're going to finish up with the optical parametric oscillator, and then if we still have a little bit of time left, we will briefly talk about electro-optics effect, which is widely used in phase modulator and amplitude intensity modulator in telecommunication. Okay, so just a little bit. Okay, let's just remind ourselves what optical parametric oscillator is. Is that we put a chi2 nonlinear crystal, okay, inside an optical cavity. This is a pair of mirror, and then this chi2 cavity is pumped. Let's say pumped with external wave E3 at frequency omega 3, right? And then the process, okay, the process is very similar to the difference frequency generation, as you have, as you will generate omega 1 and omega 2. Okay, the only difference between this and a difference frequency generation is that you don't have an input. Okay, you only have one input wave instead of two. Okay, and then the question, okay, we're going to answer is that since the difference frequency generation we have learned in last week can behave like, well, actually learned on Monday, is that the difference frequency generation can act like a parametric amplifier, okay, which if you have an input light will get amplified. Then a very intuitive question is that can we turn the amplifier into a laser, right? And we have already said that, okay, there are two key concepts in converting amplification equation into a laser equation. One is that in a laser, the z, okay, for a nonlinear equation, usually we write it down in terms of z, okay, position, as a wave propagate the nonlinear effect, convert light from one frequency to another. But in a laser cavity, the absolute position z doesn't matter because light is going back and forth inside the resonator. And then also for the laser, the only thing that you really care about is, the output. Okay, so so the first thing we did on Monday was that we convert the nonlinear equation that's based on z, convert it into an equation of t, time t. Right? It's like if you hit the turn on button, does your laser turn on immediately, and then does the laser power fluctuate, right? That's something you naturally care about when you have a laser. Okay. And the second thing we talk about is that for a laser, it's important. Well, for all the lasers, there's a critical parameter that's called laser threshold. Laser threshold is when the photon, if you have a photon inside the laser cavity, okay, after one round trip, the amount of photon will increase from 1, right? So you get effective, you get an effective amplification. Right? So only under that condition, okay, you can start from a 0 or 1 photon, okay, and then grow into a steady laser line. Okay, if your net gain is less than the net loss, then you start with 1 photon and then you slowly decay and you wouldn't have a laser action. So after writing down the equation for parametric oscillator, the next thing, a very natural thing to do is to see, okay, what is the threshold of this laser and under what condition this laser, well, under what condition the oscillator start to lace. And last time, I think we stopped at here where we write down the equation for E1 and E2. Okay, here we have assumed that the pump, okay, the higher frequency pump E3 is much larger than E1 and E2, so that you can treat it as just a number E3 here. Okay. And we have already said that this term represents linear loss inside the cavity. And also, for simplicity, I think last time we mentioned we assume the refraction index is 1. And of course, you know, this is not true in any optical system because like any media, okay, it has some refraction index larger than 1. Okay? But just for simplicity, we set it to 1 so that we don't have to carry that term around. Okay? And of course, this can be further simplified if you use the equation, well, the relationship of K, right? K is omega divided by C. Right, K is omega divided by C. Then if you use this, okay, if you use this here, what you will get is that you can, okay, erase this term, get it here. And of course, if we haven't assumed the refraction index is 1, you have to add a refraction index here. Okay. Okay. And in the note, I think I didn't make this simplification, and I carry, you know, CK everywhere. But anyway, they're just numbers here. Okay. So now let's look at these equations here. Let's look at these equations here. So first of all, when we solve a set of differential equations, we have to know for example, if the wave is propagating along z direction, we have to know the boundary condition. Right? The boundary condition is kind of the initial condition of that equation, and then allow you to get the exact solution. So when you have an equation that evolves with time, right? Evolve with time, then to get the solution, you have to know the initial condition of t, right? So you have to know the initial condition, IC, of E1 at t equals 0 and E2 at t equals 0, right? That's something you need to know if you want to solve this equation. And what is the initial condition here? Can one of you make a guess?
Are they both 0?
Yeah, exactly, right? Because there's no input. So, okay, let's put a question mark here. And I'll explain why there's a question mark here. So now, if we use this initial condition and then we plug it back into the equation, then you observe something that's, you know, very disturbing, right? So suppose we evaluate this equation at time equals 0. And the left-hand side is the differential of E1, okay? Describe how much E increase or decrease with time, t. On the right-hand side is the drive term, right? This is the parametric gain, this is the loss. And you see that at time equals 0, both of them are 0. So the equation, right, the right-hand side time 0 equals 0. What does it mean is that the differential of E1 is also 0. Right, it's like E1 is at 0, and also it's not increasing because the slope of its increase is also 0. You can do the same thing, and then you can see here is that at time equals 0, the second equation, the right-hand side of the second equation is also 0. Okay. This is very, very disturbing because that means that if you start from 0, okay, if you really use this initial condition, what happens is that your solution, okay, stay at 0 because none of them are increasing with time, right? And then you can further do this analysis. Is that, okay, if this is 0, differential is 0, then the next moment E1 is still 0, right? So it's steadily 0. So that's why I put a question mark here, okay? And later in this class, I will tell you that, okay, exactly what, why this initial condition is actually wrong, and then it is actually because of a quantum effect. Okay. Now, let's first neglect this. Okay, let's say we neglect this initial condition, and then we say, okay, then can we solve this? Right? Can we solve this? If you neglect the initial condition, what you will have is that you will have a constant, right, in your solution. And then, for example, in previous one, like when we write down general solution, like A1 cosine omega t plus B1 sine omega t, right? And then you can use initial condition or boundary condition to sort out A1 and B1, right? So let's say, okay, we neglect the initial condition first, and then let's look at this equation. Okay. The question is, do you think you can solve what E1 t and E2 t is? Okay. Can you solve it? I don't know how much you guys think about this. I kind of asked the same question at the end of last class, but the short answer is no. The short answer is no, and let me tell you why. Right? The reason is this. Now imagine your oscillator is already above the threshold. Okay, it's above the threshold. What it means is that the gain is larger than loss. Also here, okay, gain is larger than loss. Then what that mean? What that means is that the next moment, because you're having more photon, okay, you're having more photon E1 and E2, so this E2 and this E1 further increase. That means you get even larger gain, right, as time propagate. So if you really want to solve this, then what you can expect is that your solution will explode with time. Right, because it doesn't stop increasing, right? Your gain is always increasing, and then your loss is just linear, right? So if you do that, you start to see, okay, energy explode, and that doesn't make any sense at all. Okay, later we'll kind of explain why this is not the correct picture. Okay, but associated with this term here. Okay, so that's just, let me tell you, okay, from a physics intuition, you try to solve E2 and E1, okay, using these two equations. It's a dead end, okay, how they evolve with time. And the correct way, okay, if you really want to do it, the correct way is that you have to include the equation of E3, okay, E3. That's the only way that you conserve energy, okay. And you might ask, why is there a difference, right? Why can we do that in let's say a waveguide, right, parametric amplifier, but we can't do it inside an oscillator? The difference is that in a waveguide, when we derive the difference frequency generation, we also saw exponential increase, right? And why that's not a problem? That's not a problem is because the variable, okay, the parameter is z, right? It's a distance, and then the distance doesn't go to infinity, right? The piece of crystal on a linear media always have a finite length, right? So you can always, okay, say this is the length of your crystal, and then this will be the power of output, okay, in your system. But here, when you now convert it into an oscillator, things are different because technically you could have your time infinitely large. You just wait long enough, right? There's no cutoff point, right? So whenever you solve exponential increase in t, okay, that answer is not valid, okay, and that answer is not valid, okay. Now the second part is that I want you guys to look at this equation and let's say mathematically can we solve it, right? You can, like, one way that people always do is that when they can't see a physics intuition or they can't guess the answer from a simple physics mechanism, then usually what you can do is that you can just brutally solve it using math, right? And here, okay, a common way that we do it, is that you take, well, for example, you want to cancel out E2, right? You want to plug in E2 from here to here. Then one common way that you do is that you do a differential here, okay? Then this become E1, and then, okay, some coefficient, okay, and then right? So just like what we did for the waveguide. And now you have E2 now, okay, you have E2 now. So you plug in from here, and then you immediately start to notice a problem here. Is that the differential of E2, okay, is a function of E1. That's good, because then when you plug in, you replace E2 with E1. But unfortunately, it's also a function of E2 as well, right? So when you do this plug-in, what you end up with is again a function of E1, and then plus something like a E2 conjugate. Okay, so you can't simply cancel out, okay, E2. You can't simply replace E2 with E1, okay, in this equation. So that the previous method that we use to solve the coupled equation is not valid. Okay, it's not valid here. Okay, then can we take a last step back and then just think about what's the most important thing for the oscillator, let's say the threshold. Can we solve the threshold? Okay, can we solve the threshold? And the answer is actually yes, you can solve the threshold. And then there are two different methods. Well, there are at least two different methods. And and I will show both of you here. And so the first one is called steady state analysis. Okay, steady state analysis. We say that when we try to solve the threshold, and what is the physical, what is actually happening at the threshold? At the threshold, you have gain equal loss, right? That's at threshold. So what does that mean? If you have gain equal loss, that means the number of photons in your oscillator does not change, right? The number of photons that after you go one round trip, because the gain is equal to loss, maintain its own number, right? 10 photons going around, stay at 10 photons. So gain equal loss is equivalent to having a steady state solution, which means that the electrical field inside the resonator, inside the cavity, it does not change, right? Because gain equal loss. Okay, so at the threshold, you can get a steady state solution. Okay, gain equal loss. Okay, does that make sense? Okay, now if we use this, okay, at the threshold, gain equal loss, steady state. What you will get is that you will get E1t, okay, and E2t it's not a function of time anymore. Okay, it's now steady state. Okay, become a number. Okay, and then steady state means that their time differential is 0. Right. Okay, and this makes a lot of sense if you think about it. Actually, most lasers, at least the one that you can buy on the market, when it's turned on, it's actually at steady state. Okay, the laser power, it doesn't increase, it doesn't decrease, but it's a very stable output power. Okay, so that's also mean a steady state. Okay, so if you put the steady state condition back into your equation, then what you will get is you will get I, the left hand side is 0, equal to I omega 1 chi 2 E3 0 E2 conjugate minus. Okay, the second equation, again left hand side is 0, I omega 2 chi 2 E3 E1 conjugate minus tau E2. Okay. So you get this equation give you the relationship between E1 and E2. Okay. This equation also give you the relationship between E1 and E2. Okay, between E1 and E2. And both of them has to be correct, right? Both of them has to be right, because you can't have one of them as steady state, the other not, right? Let's say if the first equation is a steady state, but the second is not, then your E2 will change with time, then this term will change with time, then you will have a time derivative that's not 0, right? So if you truly have a steady state solution, then both of these E1 and E2, they have to be independent of time. Okay, so now one thing that we can do, okay, to make this equation look a little bit similar to each other, is that we can take a conjugate of the second equation. Okay, we can take a conjugate of second equation minus conjugate. So this way, you now have E1. Okay, you now have E1. And then you have E2 conjugate, right? So this two looks exactly the same now. Okay, it looks exactly the same now. Okay, then then what you get, okay, from here is that you see that this is a relationship between E1 and E2 conjugate, right? So you can move this to the left. Can move this to the left. And then you get the first equation, you get E1 divided by E2 conjugate. Okay, give you I omega 1 chi 2 tau E3 0, right? This is the first equation. The second equation give you E1 divided by E2 conjugate. Okay, and then you see that, okay, now this all go to the left hand side, so this go from here to here, so it's tau. Okay, minus I go to the left hand side, become I. Okay, omega 2 chi 2 E3. Okay. think that's right. You move this to this side and this coefficient to that side, and then tau and minus I times I. Yes, I think this is correct. Okay. Okay, so now if you look at this, what it gives us, instead of solving E1 and E2, but what it gives us is an equation about E3, right? It's an equation about E3. So E1 divided by E2 conjugate is a function of E3, and then it's also another function of E3 given by these two equations. Okay, so if we combine them, let's say the right-hand side equal to the right-hand side, right? Let's move it this part. I, okay, omega 2 chi 2 tau E3 conjugate 0. And then I cancel with I. Then what you get, okay, what you get is E3 0. Okay, this come to here. Okay, and all this coefficient go down to there. Omega 1, omega 2, chi 2 square, okay, and tau square. Okay, tau square. Okay, so we actually get, when we assume steady state, and then what's in our mind is that we try to solve E1 and E2, but instead what we get is an equation for E3, okay, equation for E3. And what exactly is this equation? Okay, what exactly does E3 mean at a steady state? Okay, this one E3 is actually exactly the threshold. If you think about it, okay, E3 provide the gain in your oscillator, and at this exact E3, okay, you will have gain equal to loss, reaching a steady state, right? So if your E3 is slightly larger than this, you will increase the gain, but the loss stay the same, right? So if you are slightly larger than this E3, then you will have your oscillator start to lace, right? The gain larger than loss is start to gain photon, right? If your E3 is slightly smaller than this, then your gain is smaller than loss, then your oscillator start to lose photon, right? So this is actually the transition point where you will have gain equal to loss, and then it's the definition for oscillator threshold, laser threshold. Okay. Any questions? Everyone understand why this is a threshold? Okay. Now, if we look at it, okay, what's important for the threshold? If you, let's say, we of course always want the threshold to be as low as possible, right? We want to use the smallest amount of energy here, and then to start the laser, right? So if you want to increase, if you want to reduce E3, okay, reduce the threshold, then what you can have is that you can, if you want threshold to come down, then you can increase tau, right? That's one way to do it. You can also increase chi 2, right? So what does it mean for increasing chi 2? That's very straightforward. When you increase chi 2, you increase the strength of difference frequency generation, right? And that we know provide the parametric amplification gain, right? So increasing chi 2 naturally increase your gain. And the second part is tau. What is tau? Tau here actually come from the linear loss, right? if tau increase, then this term decrease, right? So larger tau means smaller linear loss. And larger tau here actually, well, there are two ways you can think about it. Tau, okay, in effect is the cavity lifetime, the lifetime of a photon inside the cavity, right? So tau, if tau is very large, that means the photon can travel, okay, a long time before it's being absorbed or scattered, okay, by the cavity, right? So larger tau means smaller absorption, smaller loss, right? So the threshold here, one way to increase the threshold, as we say, by increase chi2, is to, well, one way to reduce the threshold is, as we say, is to increase chi2, okay, that increase the gain. The other way is to reduce the loss, okay, reduce the loss here, reduce the loss. That can also, okay, reduce the laser threshold, okay. So that's why in a parametric oscillator or any laser, okay, the quality of your cavity, okay, of your pair of mirror, how small the loss can be is as important as how large you can have the gain, how large your gain can be, okay, because the threshold is set by both the gain and the loss, okay. Okay, and this is kind of a trivial way to solve it. Any questions here? Okay, no. Then let's keep going, and then let's ask a very trivial question now, or obvious question now, is that, okay, what happened if my E3 is larger than E threshold, okay? Well, if your gain, if your pump E3 is larger than the threshold E3, then apparently, okay, you will have your parametric gain larger than the loss, right? So if you draw in time, as we say, time, okay, let's say this is number of photons, well, power, okay, then you can expect the number of photons inside, right, the number of photons inside the cavity will start to increase. Right, will start to increase, and then if you don't do anything, if we just stick to this analysis, then this will go to infinity, okay? But why the laser doesn't go to infinity? why you know, when you turn on the laser, it doesn't explode? The reason is that you have to ask, you know, how we get to these two equations, and then what assumption we have used, right? The assumption we use is actually E3 much larger than E1 and E2, so that we treat E3 as a number, it does not change, okay? But where does the energy in E1 and E2 come from? The energy in E1, E2 actually come from E3, right? You have to annihilate one omega-3 photon to generate a pair of omega-1 and omega-2 photon, right? So when you assume E3 does not change, it means that you violate energy conservation, right? You violate energy conservation. You add photon into omega-1, omega-2, but then you don't subtract photon from omega-3, right? So if you use, so now it's very clear, okay, why when you try to solve, okay, the E1 and E2, and they always explode in time, right? Because this equation naturally violate energy conservation, okay? Then what exactly really happened? what happened here is that when you start to generate photon in omega 1 and omega 2, okay, above threshold, right? This is let's use E squared. Okay. So originally your E3, okay, at time 0 is above threshold. Okay. Then you know gain is larger than loss in this area, and then you start to gain photon in omega 1 and omega 2 frequency in E1 and E2, right? But because this photon has to come from omega 3, right? So what really happened is the omega 3, okay, the electrical field of the omega 3 start to decrease, right? Start to decrease. And that's actually the only way that you can conserve energy, right? You have photon generated omega 1, omega 2, and then they come from omega 3. And as this process progresses, okay, the omega 3, well, the E3 will keep decreasing until it reach the threshold power, right? The threshold electrical field. Then at this point, the gain is equal to loss, right? Gain is equal to loss, and then you no longer will. Well, then you no longer generate the. Then you no longer generate new photons, and then you don't lose any photons, right? So E3 is here, and then okay. Then at the steady state, the number of photons for omega 1 and omega 2, okay, also stay the same. Okay, also stay the same. Okay, so this is exactly what actually happened when you turn on the parametric oscillator or you turn on any laser. Is that at first, okay, the system will supply a pump that is above the threshold, okay, above the threshold, and that causes an increase, okay, that causes a gain larger than loss, and then cause an increase in the photon in the photon omega 1, omega 2, okay, emission photon. And when the emission photon increase or consume the energy, okay, from the omega 3, and then the omega 3 E3 here, okay, start to drop until reach threshold. And then when it reaches threshold, now the laser is operating at equilibrium position, and the output, okay, is now a steady state. Okay, it's a steady state. Now, if we come back to how we can solve E2 and E1, okay, let's say a steady state, not any particular time, right? Just a steady state. You can see that the amount of photon, okay, you can generate at the steady state depends on what is your pump power, what is your E3 originally, right? If you start very high, then you have more photon in E2, E1. If you start very low, okay, right at the threshold, then you probably don't have, you just have a few photon, right? So in order to solve E2 and E1, okay, in order for you to solve your parametric amplifier, parametric oscillator output power, you have to include the equation of E3, okay, and then you can solve it at the steady state, okay. Any questions here? Okay, I want to quickly go over another method that you can, I want to quickly talk about another method that you can calculate the threshold for parametric oscillator and also for any other type of lasers. And then usually that's a method that, were written on papers officially. But I won't go through the math. You can look at the note in page 37 and page 38. Okay. What that is, okay, that the second method to get the oscillator threshold is not to assume steady state at all. Instead, what we assume is that because we know that if gain is larger than loss, or if there's no loss, right? If there's no loss, then due to difference frequency generation, it will start the E1 and E2, they will grow exponentially. So what we can assume is that we assume E1 having this following form. Okay. Okay, having this following form. Exponential. Okay, and then these two exponential are the same. It's because omega 1 and omega 2 photon, they have to be generated at the same time and annihilated at the same time. So if we have this, then what you can do is that you can plug this back into the time equation here, okay, differential equation here, and then you can solve what is lambda, okay, and particularly the real part of lambda, right? If the real part of lambda is larger than 0, then you have exponential growth in the number of photons. If your real part of lambda is smaller than 0, then you have exponential decrease in terms of your electrical field, right? So then you can conclude, okay, because one is that you have, one is the number of photons would decrease, so this is below threshold. Okay, and this is above threshold. Okay, above threshold. It's above threshold, your field increase exponentially. Below threshold, your field decrease exponentially. Okay, and you can of course imagine if the real part equal to 0, right? Then you will have the system right at the threshold. Okay, it doesn't increase and doesn't decrease. Okay, and if you plug it in and then do the calculation, what you can get is that this is at page 38. What you can get is that you can get a solution that looks like this. Okay, you get a solution like this, and as we know, okay, as we all know, this is a loss term, right? This is the linear loss term. Okay, so this is a loss, and so this is what's left here. Okay, this is the gain. Okay, this is the gain, and so when you have gain larger than loss, you're above threshold. When you have gain smaller than loss, you have below threshold. Gain equal to loss, you're right at the threshold. And if you plug in K, okay, and then simplify this equation, you will get exactly the same threshold. Okay, you will get exactly the same threshold. And the benefit of using this way for calculation is that you actually can derive the gain, okay, the absolute gain here. Okay. Okay, now let's come back to the question we asked at the very beginning. Okay, initial condition. So, as one of you have guessed, right? The initial condition is E1 and E2 equal to 0, right? At the classical case, in this classical case. And if you have that, then you have E1 and E2 always 0. Nothing will increase, right? Because your gain term always 0. So now the question is, how does it really start? How does this parametric oscillator really start? The reason that it starts is actually that this initial condition is wrong. Okay, this initial condition is wrong. The fact is that, of course, there's no photon inside the cavity, right? There's no omega 1, omega 2 photon inside the cavity. Otherwise, it will become an amplifier. Okay, so this is the correct initial condition. That, well, no photon, omega 1, omega photon are there inside the cavity at time 0. Okay, however, that doesn't equal to, this doesn't equal to, okay, E1, E2. Okay, it doesn't equal to E1, E2 equals 0. The reason is that we'll actually talk about this in much detail in the second half of the semester. The reason is that there is something called vacuum fluctuation. Okay, it's fundamentally it's a quantum effect. So in quantum mechanics, I don't know if you guys heard of the Heisenberg uncertainty principle. The Heisenberg uncertainty principle tells you, okay, in many forms. One of the forms is that, let's say there's a particle, and then you want to know, let's say there's a particle moving around the space. Then, of course, from classical physics, you will assume, okay, the particle have position where it is, and then also have a momentum, okay, the speed of its motion, right? With these two information, you think, okay, and then I can describe the entire motion of the particle in classical physics. But Heisenberg uncertainty principle tells us that, in fact, you can't know the position. Well, actually, it's not you can't know. Is that the particle itself, okay, doesn't have a certain position and momentum at the same time. You cannot have that. Right, so if your particle has a very certain position, which means the delta x, the uncertainty of your position, let's say approach 0, then your delta p has to approach infinite. H bar here is a constant, a Planck constant. Okay, and what does this have to do with us here? What you can see in the second half of the semester is that there's also an uncertainty principle between the electrical field and magnetic field for the Maxwell equation. Okay, so so what that means is that you cannot know your electrical field for sure. You cannot know 100% of your electrical field. That also translates into you cannot say your electrical field at time 0 is 0. Okay, because if you know the time, if you know the electrical field is absolute 0, then your magnetic field is completely uncertain. And then you know that, okay, if you plug into Maxwell equation, if your magnetic field is completely uncertain, then that will translate into a changing electrical field. right? So even if you assume, okay, this is 0 at this moment, the next moment it will not be 0. Okay, so so the fact that you can have 0 photon but still have non-zero electrical field, okay, is the reason that your parametric oscillator can actually start. And I know the next very obvious question is, okay, let's say if I say E1 is at a certain number, E1 a number C, okay. But doesn't that violate energy conservation? Like if you give a certain energy to the, if you get certain amount of electrical field that carries energy, right? Doesn't that violate energy conservation? The answer to that is that what Heisenberg certainly told us is that it's the uncertainty of this cannot go to 0. What it doesn't say is that whether you can have your time average, okay, of your certainty goes to 0. Let me take, no. What it doesn't say is that, it doesn't say that your average, okay, time average of your field cannot go to 0, right? So if you look at the energy conservation, okay, and its relationship to Heisenberg certainty, what it is that in the short term, okay, you have a lot of fluctuation. That's why you have the uncertainty. Okay, but then when you average all them in terms of time, okay, in the vacuum, you will see that the average value is 0. Okay, I don't know whether you two have seen the movie Avenger. I think it's Avenger 4 or 5. Well, not 5. Avenger 4. I think there's a time that there's a scenario where the Ant-Man, okay, go into a time machine that they say built up from quantum fluctuations and then can travel back in time. Okay, of course that's wrong, but then they kind of the concept they're trying to make sense of it actually do exist. Is that if you look at a very small time scale, then there's actually a quantum fluctuation, okay, and then there's uncertainty, okay, and that's why you can have a non-zero E1 as your initial condition, even if there's no photon, okay, even if there's no photon. Any questions about this part? Okay, so now let's talk one more thing about the parametric oscillator, why it's so useful in quantum optics. Okay, the reason that it's useful is because if you look at it, the omega 1 and omega 2, they have to be generated at the same time, right? Because that's the only way that you can annihilate omega 3, right? If you only annihilate omega 3 but don't generate, and if you annihilate omega 3 and only generate omega 1 and not omega 2 at the same time, then you violate energy conservation by a lot, right? So the photon, okay, is always co-generated. Okay, so below the threshold, this process happened kind of randomly. Okay, randomly emitted photons, and then they are in pairs. They're in pairs, and so there's actually a quantum correlation between omega 1 photon and omega 2 photon. For example, if you try to measure the amplitude, or you try to measure the photon number at the output port, okay, this is omega 1, omega 2, you'll see that the number of photon in omega 1 is identical to the number of photon in omega 2. Okay, and then also the electrical field of omega 1 is strongly correlated with the photon, or with the electrical field at omega 2. Okay, so what this is actually something called entanglement. Okay, entanglement. And of course, this is a quantum electronic class. It's not a quantum computing class. So we're not going into detail to tell you the difference between entanglement and classical correlation. That part require the knowledge of quantum measurement, and superposition. But this is this is how you create entanglement in a quantum experiment with something fairly straightforward, fairly that you don't need a lot of quantum knowledge to get this. And also another thing is that when omega 1 equal to omega 2, you can tune that by changing the phase matching condition. Then what will happen is that then again the photon is generated in pairs, but then they are indistinguishable, right? Omega 1 and omega 2 are the same. Now this corresponds to a photon state, a state that only have, let's say if I write this down as number of photons. There's a probability of the number of photons, and you see that there's only even number of photons. There's no odd number of photons being generated in this case. And what people have found is that if you generate this state, then the electrical field can have very small fluctuation. Of course, that that means another. Well, here actually the fact is that one quadrature component of the electrical field has very small variance, and then the other one is very large. And people have been able to use this to enhance quantum measurement, for example, the detection of gravitational wave. Inside there's actually a very nice parametric oscillator that generate omega 1 equal to omega 2 light. And then this created something called squeezing, and to help the detection of gravitational wave. Now we have 15 minutes left. I will quickly go over any questions here. So we have 15 minutes left. And then I will go over the electro-optics effect, which is a backbone for optical communication. So the definition of electro-optics effect, you can turn to the note, page 39, is that one can use electrical field. It can be a DC field. It can be an oscillating field like microwave or millimeter wave or radio frequency, wave, to change a refraction index of a dielectric material. So if you have a piece of dielectric material here, and then you have light coming in, and then if you apply an electrical signal here at the voltage, even it can be DC electrical field, RF field. This side is grounded, right? Then in between this capacitor, you will have electrical field here, and you will change the refraction index. This process is called electro-optics effect, using electron to process optics. It's very clear how this can be used for telecommunication, right? The electrical wave, let's say in a cable, right? It couldn't transmit very long distance, right, because of the loss. On the other hand, optical wave can. Right? Optical wave can travel hundreds of kilometer, okay, hundreds of miles. So, but all of our computers are actually made from electronics, right? So if you want to transfer information from one computer to another computer that's locally very distant from each other, then what you have to do is that you have to convert your information from electrical signal to optical signal, and then load it onto the optical fiber, and then send out to the other side. And then when the people receive that, they will decode it, right? Transfer the optical signal back to electrical signal, okay, and then read out on the other side of the computer. And this effect, I think, will be taught in details in Andreas Berlin's optical communication device class. So here, what we are going to talk about is simply, okay, what type of nonlinear effect can cause this? Okay? And the nonlinear effect is actually precisely the second order nonlinear effect. Right? You will have, say, your displacement field, of course, is this. Refraction index E plus P nonlinear. Right, and then your P nonlinear is epsilon chi 2 E squared. Right. And now let's define E, okay? Now the electrical field has two components. One is from your light, okay? Let's call that E. Okay. The other electrical field is from the it's from the low frequency electrical voltage, right? Let's call it E prime. Okay, and this can be varying with time, of course, much slower, okay, than the optical oscillation frequency, and then complex conjugate. Okay, so okay, E and E prime, and then if you plug it in here, you'll see E plus E prime, okay, plus E conjugate plus E prime conjugate, and then square. Right, and then square. And you know that there's harmonic components, and then like the square of this, square of that, square of all this, and that doesn't matter. What matters is a cross term, because the cross term tells you the interaction between this voltage and this light here. Okay, and that would be E times E prime, okay, plus E times E prime conjugate, right? And of course, times plus the conjugate of these two terms. This with this, this with this, and this with that. And if you take a closer look, okay, this is actually equal to E2, okay. I think I missed a factor of 2 in my note. Real part of E prime. Right, if you have a variable plus its conjugate, it gives you twice of its real part. Right. So then if you plug all this, and then of course times conjugate. Right. So if you plug all this back into the displacement field, and then let's ignore the epsilon. Let's ignore the vector here. This would be epsilon r E, okay, plus this term here, okay, is the 2 epsilon chi 2 real part of E prime, and then E. Okay, and now if we look at this, okay, we find that there is a common factor here, E. Okay, that's coming from the common factor is here. So then you can write the other things all together, epsilon r plus 2 chi 2 re. Okay, you can include the frequency term now inside. Okay, so it looks like, although this is a nonlinear effect, right? This is a nonlinear effect, but it looks like the net effect is that you change the relative permittivity, right? By applying a voltage, you change the relative permittivity, and we know that epsilon r equal to n squared, right? So equivalently, this nonlinear effect actually change the refraction of index, okay? And you can make a few assumptions to make this you can make a few assumptions to actually derive a much nicer relationship of refraction index. Okay, so n is square root of epsilon r plus 2 chi 2 re. Okay, and then we can assume that this effect is very small, so that the refraction change caused by the added electrical field is much smaller than the original, permittivity. Then this one you can use you can use approximation that 1 plus x to the n, 1 plus nx. Right? So you cancel out the 2 here, and then you have okay. Okay. So this part is the original refraction index. So this is n0. Okay, this part is the change in the refraction index. Okay, so delta n now equal to chi 2 . I think I missed a few coefficient here. Okay. Anyway, you can look at the note, but the basic idea is the same here. Okay. The basic idea is you can apply electrical field and then it change the relative refraction index. Okay. And if you change the relative refraction index, then you know that when the light propagates, it's I omega t minus I kz, right? And what is kz? K is n 2 pi n divided by lambda times z. Right, so now if your refraction index change, okay, the output field, let's say the length is L, right? So it becomes 2 pi n knob L divided by lambda, that's the original one, times epsilon minus okay, I 2 pi delta n L divided by lambda. right? So the output will have a phase change, okay, compared to when you don't have a voltage applied to here, okay? So that's why, like the very first device you can create from electro-optics effect is a phase modulator. Okay, it's a phase modulator, and this has been, well commercialized, and you can buy one for a few $100s. Okay, and also you see delta N is proportional to E. Okay, real part E, but you can apply a real E here. Okay, and that's let's say the delta phi proportional to the E you applied, right? But as you guys probably do electrical experiment, you rarely measure the electrical field, right? What you actually measure is, for example, something like current, voltage, right? Things like this. So here, one thing you can do is that, or it's actually often used in the industry, is that we don't use E, okay, as something proportional to the field. Instead, we convert E into a voltage, right? For example, E, the voltage, times the distance here, D, okay, give you the voltage, right? That's the basic equation. That's a basic relationship in a capacitor, right? So delta phi will now proportional to the voltage you apply, right? And now this is much more closely connected to your electrical experiment, right? Because you can create all kinds of voltage, and then you can measure voltage directly on a oscilloscope, okay? And something that when you buy a phase modulator, okay, something you would notice on your spec sheet is something called a V pi, okay, V pi. What V pi is the amount of voltage you have to apply so that you can change the phase from 0 to 2 pi, from 0 to pi, right? From 0 to pi is the maximum difference that you can make for electrical field. Right? If you change from 0 to 2 pi, then 2 pi is again 0, right? So this is a number that people use all the time to kind of characterize the performance of their electric optics modulator. Okay, we have 1 more minute. Let me finish up by how to build how to build intensity modulator from phase modulator. Right. So what you do is that you have a light coming in, and then you split 50-50, okay, into 2 parts. One has a phase modulator. The other part has nothing. Of course, the actual modulator doesn't look like this. Okay, and then you combine them. Okay, so on this path you will have your original wave, right? Okay, this is on the lower path. Okay, this is nothing changed, so it's 1. On the upper half, you have a change of phase, right, which is proportional to I pi V, okay, divided by V pi, right? So that you can clearly see now, if you apply V pi into a modulator, that you change the phase by pi, so that this term becomes -1. So you have 1 minus 1. Okay, now becomes 0. Your output is 0. But if you have Vt equals 0, then it's 1 plus 1 divided by 2. Your electrical field is the same as it is, right? So by applying a voltage, okay, you can change the output of the light from 0 to 1, okay, and 1 back to 0. Then you convert your electrical bit into an optical on and off bit, okay, and that's what people do in optical communication, okay, and that's it for today.